We're going to talk about the continuation of what we showed last year here at Smalltalks, also at ESUG. This is pretty much, it's not the same presentation we just did at ESUG, but it's that presentation plus a few more things we just did in this last month. You can tell which one of us is who from the pictures. So last year we talked a little bit about how we started doing this. Well, we both worked on security for a long time, like roughly probably 8 years, 9 years together, something like that. And we are both small talkers for a long time too, like more than 10 years. Way more than 10 years, I think.
10 years.
10 years, for instance. Yeah, so we were interested in security and Smalltalk, and we wanted to evaluate the security of the Smalltalk systems we were using. I personally started doing Smalltalk with DigiTalks VMs, and it's a very simple VM. And I wanted to use a cheat VM also, because I'm very interested in security of virtual machines, like Flash virtual machine. I want to understand it better. And I knew a little bit about those flows in Flash. So I chose that VM because it's simple. It's the first one I use, so I kind of have some attachment to it. And so we went deep into it. And the kind of bugs I'm interested is binary bugs. So last year we presented how we managed to escape from the VM into executing native code. And to do that, we had to understand how bytecodes are translated into assembly. I think this is not new for you, because Elliot already talked about that. Leandro talked about that a little bit too. So we managed to disassemble the Smalltalk code, and integrate that into the environment. So now we can, for example, we can see now the. Well, no, we can't. No, this. If we look back there, yeah, we can see now how Smalltalk is compiled down into assembly from the browsers, right? And here we can see the Smalltalk and the bytecodes, and now we can see also, this is a new version, we can see the Smalltalk. Assembly, bytecodes, and Smalltalk, all in one window. And this is very important for us, because to escape from the VM, we need to understand the details, and we need to understand how to manage to make the processor things it's not supposed to do. So last year we focused on that. This year we're gonna go a little bit farther. But I want you to understand that to do that, we had to understand every bytecode, what every bytecode does, because we want to understand how to manage to trick the VM to do assembly code that we want. Okay, so we needed to understand every bytecode. So we had to document every bytecode, how every bytecode is translated into assembly. And of course, we chose to document that in a dynamic text editor like Smalltalk. Okay, so we documented in Smalltalk, and we end up having working code. And now I'm going to make a stop, because I heard that this is not very clear. The end result of this documentation is a just-in-time compiler that works. Okay, so we have a just-in-time compiler that works. That written Smalltalk, right. Written Smalltalk. We have a hierarchy. Every bytecode is a class. Every bytecode knows how to translate itself into assembly. So we ended up with the just-in-time compiler that works in Smalltalk, and this just-in-time compiler can translate bytecodes into assembly. And the Smalltalk compiler knows how to translate Smalltalk into bytecodes. So the full chain is that now from Smalltalk we can translate Smalltalk to assembly. So there we stopped and thought, okay, wait a second. Did you just say you have a translator from Smalltalk to assembly? Oh yes. So that means we can create executables or DLLs from Smalltalk, right? Yes? Well, let's try to do that. So we thought, okay, as everybody wants, who doesn't want to write a VM? That's what I guess. Nobody raised their hands. So everybody wants a VM. So do we. So we thought, let's write a Smalltalk VM. But you know what? Let's write it in Smalltalk, because we can translate a Smalltalk to assembly. Okay? And we want to use the iterative process that we learn with Smalltalk all the time. So we want to be able to test the parts by themselves. We don't want to wait until we have a full working environment to test it. We don't even want to wait until we have the object memory implemented to test the shit. And we don't want to wait until we have the full shit implemented to test the garbage collector if what we have is enough for us. So we say, okay, let's leverage the environment in which we are implementing our VM to test our VM. So for example, we're not at this phase writing the full GC. We're using the GC of the environment where we are running. And we're not writing the primitives. We're using the primitives of the environment we're running. I think this is kind of similar to what Aishi taught. Angel is going to show us in the last talk of the conference, I think it is, where he leverages the .NET running environment to write on a Smalltalk. This is pretty much the same. We are using a Smalltalk environment to write a Smalltalk VM. So to be clear, from now on, this has changed. We are now writing a VM. This is a different project, okay? We still find security problems because we can't help that. But now we're running a VM. And so far, we've got a sheet that works and a little bit more than that. So what is a VM? It's more than that. We ask Andres for advice on what is a VM, what do we need to get a Smalltalk. We ask the community, we put that on the list. It's more than this, but we wanted to test things part by part. So we wanted to generate a DLL from our Smalltalk code so we can build an environment from our DLL and the environment we have all together and make one big system that works. So we needed to write down executables. DLLs and executables are the same on Windows. So we had to write a framework to write PE executables on Windows. We have to have some kind of method lookup because we want to write in Smalltalk and want it to be polymorphic. I didn't say dynamic on purpose, right? We need to understand the object format. At some point, we have to go down and do the memories management, that GC, creating objects, copying objects, maybe become, if we support become. At some point, we have to do the primitives, FFI interface, processes, callbacks, everything that takes a Smalltalk, right? VM. So, first thing I say we wanted to do is to be able to, I'm going to introduce a term, like freeze Smalltalk code down into an executable. That means translate the Smalltalk code into assembly and put down that into an executable and freeze, because we're here in this step, we're losing the possibility of changing the system dynamically. We cannot, so far, we cannot add new classes. We just want to do one step at a time. So, okay, this shit is working. Let's freeze it. And now let's use that binarily to ship more stuff, okay? So, this is the interface to the big nativizer. You tell it to, okay, I want to freeze all the methods in this class, the GZ space. And I want to add all the methods on the object generation on GC. Or that object doesn't go. It's on the generation on GC. And at this particular selector, I want to add this class. And at this selector size down there, I want to add these two classes. This means that my system, while frozen, is going to use only this code. And it's kind of tricky to find what we call the closure of all the Smalltalk code that we need to freeze, so this code does not need to go out down to the VM to keep executing. But we solved that. And we have something else like in the last line you see at this particular selector, we want to add this particular implementation of the method for every receiver. Or the default is a little bit more than that, but that's enough for you to understand. It's the default for this selector is this implementation. Okay, so in metamorphic cases, we don't need to do a lookup if we know it's metamorphic. We just jump to that one. Or when the cheap lookup we have fails, we just jump to that one because that's the default. Okay. So thanks to Elliot, I think this is going to be easier. This is from last year, but this is kind of normal lookup on a Smalltalk. Before evaluating the method, you need to know if the actual receiver is the receiver at the time where you nativize that method. This is using Elliot's presentation when you have a monomorphic call site or even polymorphic. In the prologue, he compared the class that's attached to the call site to the class that was used to nativize that method. Okay, and if it's not the same class, then we need to do a lookup in the worst case. Okay, but otherwise I can keep executing. So this is kind of a graphical representation of two methods that have their own prologue where they check the classes. So a little bit farther than that is something that today Elliot showed us, the closed polymorphic inline cache, where he changed the comparison for several classes, and on each one he jumps to the particular implementation. Okay, so we move the class of the receiver to a register, right, to a variable, and then we check whether if that's object, then we jump to the specific implementation for object. Otherwise, we jump to the specific implementation for undefined object. Okay, and otherwise we just trigger a lookup. But then we added a little bit more. We said, okay, I don't want to trigger a lookup. I just want to add a default implementation. So we just hard code the last path on the polymorphic inline cache, if you want. We used to call this multiplexer because it multiplexes for classes. One selector, many classes, right? And then we went a little bit farther, and well, it's not farther, but we realized we have not done it before. We added a particular case for small integers because they don't have a class, so it's a tag check. So we added it. Okay, if you want to do something for small integers, the interface is the same, but the generated code is a little bit different. It doesn't have to check the class. It checks the tag bit on the receiver, which is 1, by the way. Yeah. So, and then we've just added one more thing. So we were saying, what happens if all the class checks fail? Then either do the default or perform a lookup. And we just had an interesting idea, and Javier sat down to test it, and so he implemented one more trick into this cheap lookup mechanism. And it's when every specific check for each class fails, we fetch the superclass of the receiver and jump back to the beginning of this multiplexer. And with this, we've got inheritance. Okay, it's a very, very cheap way to get inheritance, and it works. I mean, it's cheap because we had the framework to do it, right? We just had to do this, and the code to do it was surprisingly simple. If we get there, we're gonna see it. Changes. So. Again, I want to stress that this is not a dynamic system. We get all the methods we're going to execute during our native code and freeze it. So this inheritance is only inside that freezing code, okay? And this is the implementation. The multiplexer, remember I said we call multiplexer what Elliot called the polymorphic inline cache. And here we added at the end, after rendering the jump for every class, we added the load next method dictionary array in chain. Okay, the Smalltalk we are using as framework and the Smalltalk we are implementing does not really use class pointers, but uses a direct pointer to the array of all the method dictionaries in the hierarchy. That's a simple optimization and has many very interesting side benefits. So how is load next method dictionary array in chain implemented? Okay, this is what we're going to do if everything fails, so we get to get super and jump back to the loop. So it says gets from the receiver the method dictionary and put that into a temporary variable.
Because we have the method dictionary array and we need the method dictionary from the actual class.
Right. Remember, we originally, before entering this multiplexer, we moved the method dictionary of the receiver into a register. So we start from that register. So we have the method dictionary of the receiver in a register. So from that method dictionary, we load from that method dictionary array, we load the method dictionary, okay? And that's, I'm gonna lie a little bit, but that's just an instance variable. It's the first slot in the method dictionary array. The first slot of the method dictionary array is the method dictionary of the receiver. So to load the method dictionary array, it's a third field, okay? It's not the first, it's the third field of the method dictionary array. This is the class, yeah. So the first, it makes sense. The first field of the method dictionary array is the method dictionary. So let's go back to here. And then so we then load the class from the method dictionary. And the class is the third field of the method dictionary. So we load the third field. And then we load the superclass. From the class, we get the superclass. Okay? And the superclass is the first field of a class. So we are dereferencing the object until we get the superclass. And now that we got the superclass, we're pretty much done. And we just, okay, we don't use the superclass. We need the method dictionary array of the superclass. And that's another field in the object. And then after that, we jump, we continue. And since this is we continue on loop, right? There's a jump back up there. And then here you see that for every load that we did, we check whether it's nil. Because there might not be a superclass, there might not be, we make sure that everything we are looking for is there. And then if one of those is nil, then we just, in the multiplexer, compare the result with nil. And if it's not equal, we jump again to the table, to the lookup. And otherwise, we fall back to the default, right? So with this, we had a very cheap and working lookup mechanism that we can use. Now we got polymorphism in our frozen code. And remember, the whole chain is Smalltalk code, pure Smalltalk code, using the compiler into bytecode, pure bytecode, Smalltalk bytecode into assembly. No restrictions in what you can compile, except for that you might not be able to create objects during GZ, for example, but that's reasonable, and you can overcome that. But it's pure Smalltalk. So our JIT is written in Smalltalk. We have lots of tests for that, and then we kept going with this idea of creating a VM. So we implemented writing PE files. And that took us a lot of time because PE files are very complex, right? But we have code to write PE files with their directories, sections. We can put code into that. And the main interface, remember, is, okay, I want to freeze everything from this class and this particular method, and all this, I want to freeze that into one DLL or one executable, okay? And we can say things like, and I want to add an export for this symbol and this symbol and this symbol, so we can create executables. And then there is a little bit more than that. We need to, okay, the next step that we want to do is, that we're going to show now, is to write the GC. We want to write the GC in Smalltalk. And we've done it, and we're going to show it to you. But you can understand that to write the GC, we need to, for example, request more memory from the operating system. And there's no bytecode to do that. We need to have some kind of FFI, right? Some primitive kind of FFI to ask things to the operating system. And we also need to access things from objects which are not normally accessible, like the object flags and the header of the objects. And those things you usually cannot access from Smalltalk, so we had to add kind of primitive things that we call under primitives, because all the method names start with the underscore, and it's kind of a lower level. With these primitives, with these under primitives, we're going to implement primitives later, so it's kind of a lower level. So, for example, here we have commit, and in commit, to implement the under primitives, for some of them, we just talk to the assembler. Okay, we tell the assembler, load this register, push something, and then call down here, call virtual log from kernel 32. And this is all frozen in one method that is translated into assembler. Okay, so this is code that is evaluated at compile time. It could be a pragma maybe
this looks very simple, but actually it creates an import table. It solves all kind of preferences in the P files. And it's really hard, and it's just a single line of code.
Yes, yes. Our framework is we work a lot in the P framework. So now it's simple to import a function and call it, and that's because we put a lot of work in the other part. And so we move forward to implementing the GC. Okay, and here until now we talked a little bit about, we picked up what Elliot said, and here we're going to start picking up on what Andres said. This is great because they paved the way for us. So
yeah, and so well, we try to move the object of the GC into first class object, and we need the spaces, as Andres said yesterday. We can add things to the spaces, and actually we do ask those things, like, okay, we have the info of an object, and we want to know if this object belongs to this space. And also we can make a shallow copy. What?
no, shallow. Sí.
Okay. We can make a shallow copy, which do actually that. Just make a copy on this new space. We are going to use that in the generational GC. And this is important, this here. This is the most important thing of the collect of the generational GC, which is just follow the roots, the remember set, and the literal references, walk the stack, and then rescue ephemerals, traverse weak containers, and those things. Okay. Finally, flip the spaces. That's important.
I want to make sure you understand this. We're implementing the GC, okay? So what you're seeing here is not just Smalltalk code that models the GC. This is the GC.
Yeah, this is the actual code.
It works. We're going to show you that it works. So we're implementing it in Smalltalk. I'm repeating this because apparently it was not clear. We are implementing a VM. Okay, so this is the implementation. What you're reading now on the screen is implementation of our garbage collection.
Maybe it's clear to explain that, for example, what we saw with Elliot, then to run that VM, you need to compile and...
We're going to do that.
Yeah. See, in this case, you directly implement from image side.
Right. We're going to show you how we test it, and you're going to see what we mean that is working. Yeah.
No, we can do that now.
Yeah, why not?
Yeah, we can...
Well, luckily you won't see it working. Yeah. Because it's invisible, right? If everything works, you don't see it. You just have to trust us. Okay.
Okay, now it's working.
He just what he just did. I think we can show a little bit of that code.
Put it hot. I want to see.
No.
We can put it hot actually. It's an under primitive, but we need to attach a native debugger.
No.
So what this does is well never mind. But it creates a DLL. It dumps all the code for the GC in the DLL, brings the DLL, loads the DLL into the process, and then tells the environment, you know what? I want to start using this particular generational GC, not the one you were using. I want to start using this one. Okay, and then now we have a VM that's part of the VM is the environment we use for developing, and part of the VM is what we are developing. Okay.
Okay. So we want to follow the object, follow root and walk stack. We just follow every object we found, and we just.
So following the object is for a GC is you need to traverse every object and see if it's alive, right? So you start with the roots of the graph and you follow every point. This is the implementation of that, okay? And it's a recursive function in our case. We will change that probably later, but today it's a recursive function. It works.
Yeah, we have some issues. Andres say some issues yesterday, and I say, yeah, I know. I have the same issue.
Yeah, if the graph is too deep, we run out of stack. Okay.
And the roots were stored.
It's a global array.
Yeah.
It's a remember set. That's
the small thing in Andres' graph of the.
It's a remember.
The remember set.
In Andres' slides, he had the spaces with the block with remember table.
Remember table.
RT.
Okay.
That's a remember table. We call it remember set.
That's the remember set. If we found some weak or ephemeron, we just keep those references for further computation. And follow, this function here, follow, is this one. We just take all the fields of the object and check if the object has been moved. Okay, if the object is in the front space, and we are interested only on those objects, yeah. Okay, we are going to do something.
We have, from the point of view of the generational GC, we call the two spaces we have the from space and the to space, because we're going to move things from one space to the other. So, yes, edit.
Sorry. So, Richie, if you change the implementation while you're running, you generate a new DLL loaded at a different address.
We're going to show that.
Oh, okay.
Okay, well, its proxy means that the garbage collector has already moved this object to a space, so we set a flag there, and we put the address of the new object, so we just change objects there.
In other slang, they call it the forwarder.
The forwarder, yeah.
Proxy, forwarder. Well, we need to just. We don't know about GC actually.
Yeah, we are learning. And with containers, this is very simple actually, because a weak container has a reference that is weak. So it means that if the garbage collector hasn't moved the object, this object has to be removed. So we just look for all the object in the weak container, and if the object is in the front space and hasn't been removed, we just put a residue object here. So it's simple. Ephemerons, which we implement highest work on ephemeron, and it's quite different to the implementation, but it's similar to the implementation in the paper. Finally, we flip spaces, which only is just change the pointers, just the contents of the variables, and testing.
So testing of all this is very, very interesting. Because you know what a GC needs to do, right? If the object is not referenced, it should go. If it referenced, it should survive one generation. And in our case, if it survives 2 generations, it should move to the old space. And we want to test all this, and we also want to test ephemerons, and if the ephemeron is not referenced, it should go away, and all those kind of things. So we've got tests for all that, okay? And this is pretty much how our tests look like, if I can manage to use it good. We said I was going to use my mouse, but I forgot. So here, after follow roots, okay? After following the roots, we should have marked all the objects that are referenced, and we should have released all the objects that are not referenced. In fact, after following the roots, we should have all the objects that are referenced already in the 2 space, in the second semi-space, and all the other objects that are not referenced gone. So at the end of following the roots, and before all the rest, before flipping, but just this test just tests follow roots, okay, one particular object. The difference between what was the new space and what is now the new space in bytes should be the size of the objects that has just gone, okay? I mean, some objects died, the difference in size of the 2 semi-spaces should be that. So let's see the asserts. Is the flip size less than the current size? Well, that's a weak assertion, but nonetheless, it should be true. And then if it is, then we specifically test that the object that we use as a bait for the GC is gone. So we up here
we populate the front space.
We build the spaces we want to use. So we have the front space, and in the front space we shallow copy a string into that. Okay, so we populate the front space, and then we put some other strings. We put another string, and then we put an array. But we have this array that references the number 1 and references this string and references this array, and then we use that as root. So this string and this array are actually referenced, but this copy of the string leaf is not referenced. So this one should go. And in fact, this is what the test does. Okay. So here is our test for the GC. There is a small detail. Okay. Any questions about that? This is how our tests look like. We populate the spaces with some particular patterns, and we test that the objects go away or survive or become weak or gone. So this test we need to execute, sadly, because of the under primitives and because we are accessing the flags of the objects. We need to execute these tests natively, not in Smalltalk. Okay, this is something we need to figure out how to fix. We would like to execute the test in Smalltalks and natively. So to execute the test natively, we came with a particular language, and it's execute this block proxying this object. So we freeze all the code for the GC and then give that code one particular object where this frozen code, native code, needs to use as receiver, for example, or as object, right? So this is just part of the framework we're using for testing, but it's because we are actually testing this natively. We are sure that our code runs natively, which is what we're more interested. We want to test it in Smalltalk so we can debug it easily, but so far we're testing that it works. Okay.
Sorry. Yeah, but this execute proxying actually sheets the code, builds a DLL, load the DLL, and everything.
Behind the scene, it does lots of things.
Yeah.
Okay. Okay. This test we've just done, we installed the generational GC, and everything kept working. But now we're going to make a modification to the GC. and reinstall it. Okay, so far it's not like fully dynamic in the sense that you can change the GC during while it's running and it just works. So we have to make a change and reinstall it. Okay, and I think that for some parts of the system we're gonna have to live with this limitation, like the GC maybe, because if we change the GC while the GC is running, you can expect weird things to happen. But we're not sure. We're not completely sure. This could be lazily translated. Maybe the GC could be lazily translated. We're not sure so far. It might be possible. Yeah.
Because you showed that what happens if you have two completely different implementations of the GC?
Count GCC.
Good. So what we're not doing now, just a second, while we're talking, he's adding a counter to count how many objects are moved either from the front space to the to space or from the front space to the all space. Okay? He's adding a counter to have statistics to the GC. So he added an instance variable to the class generational GC that's called counter. He added an increment when we copy an object, and he added an accessor, okay? And he just installed the generator. He's about to run it. He's about to inspect it. Well, he's not. He's just going to inspect the current GC, and he's just going to see if the counter is moving. Yes, it's moving. It's 9:25. Okay. So we just changed the GC. This is a silly example to show you that we are actually using that GC, okay? And that you can, it's not fully dynamic in the sense that we're used to, but it's still very dynamic in the sense that we're not used to with GCs. Okay? Yes, you had a question.
My question was, what happens if you have, for example, a GC that is reference conflict, and then you want to put a GC that is generational currently? Can you do that or no? Well, you have to change, to move all
the question is, he asked, what happens if I want to do a counting GC? I'm not sure, but I'll tell you, we haven't thought about that because you have to change the object headers probably. It's a big change. But suppose we wanted to implement what Andres showed us yesterday. We wanted Eden with two semi-spaces. That's kind of just it's a different kind of generation of GC. Yes, we could do that. We were talking about that, and we think it's possible for us to implement a different generation of GC that maintains the same functionality at this point, right? And install it. Yes, that could be possible. Absolutely. We think it's possible to do that.
Yeah.
So the thing is that requires what's called an image tracer, right? The Smalltalk tag forever because you have to change the object representation. So you do that by finding your root object, which is Smalltalk, and tracing the current space. And you write a new image, right? And then you deploy your new thing. And now when you start up that process, you have two players and you just kill this one, right?
Absolutely.
But it's more complicated because you have to munge the object.
Yes. In our case, we would write the object tracing in Smalltalk, of course. And I'll tell you more. The GC is already traversing the graph. So I would use the GC to write the object tracing, right? And maybe we don't need to create a new image, and maybe the two object formats can live on the same image. So while the GC is copying the objects, maybe you can translate them, and you get a hybrid. It's hard to do, right? But if we want to keep it all alive. Yes, so the next example, because we don't want you to forget that we also wrote a JIT. So the next example is show in 5 minutes, of course. It's while he's doing it, I'm going to relay. I'm going to talk about what he's doing, okay? It's 7 actually, 7:27. And so what we're going to do is another example to show you that we can change the just-in-time compiler and use that, okay? So what he's going to do, he's going to add coverage. He's going to add support. He's going to add coverage support to the VM by changing the just-in-time compiler, and pretty much what he's just filed in the changes, right? But the change I think is interesting It's a difference in the prolog for every compiled method, for every native compiled method, yes, that the prolog is going to patch the prolog itself. Okay, we need a place where to store a flag to see whether the code was executed or not, and we use the integer test in every prolog to store that, because our integers are 1 tagged, but actually 2 bits are left. So a tag of 3 means that the code was executed already. And the same test works. It's actually, checking for a tag of 3 means that the code was executed already. Checking for a tag of 1 means that the code was not executed. So this is self-modifying code. So he just installed it and ran it, and he just asked for all the uncovered method. Okay, we are now doing coverage on the GC. Okay, we nativized the GC with our JIT, modified JIT, to do coverage. We installed the GC with our modified coverage GC shit, DLL, whatever, and then we get all the uncover methods. And one particular uncover method is the fixed references or set timestamp. That's only used when a weak object goes away. Okay, when you need to, or actually doesn't go away. So if you create a weak object, and then if there's a flip, and then if you get again the uncover methods, we should see this method go away from the list of uncover methods. Okay, and in fact it goes away. Okay. So I think we're pretty much done with 4 minutes 42 to go. Let's see what else we have. Before going there, I'm going to try to go over what we just seen. We started doing security review because we love breaking things in the sense of security. I mean, it was part of our life for a long time. But we understood that we were doing a lot more than that. We were documenting the just-in-time compiler in a way that works, so we ended up with a just-in-time compiler. Now we have a just-in-time compiler that works and that can be changed and is all implemented in Smalltalk. Pon la jerarquía de las clases, de los micros, ¿no? Yeah, and then we said, okay, let's test if we can use this just-in-time compiler as we think we can to build another part of the system. Let's go for the GC, because we know the GC will need lower level access to the VM, to the objects. And it will require from us to implement more things. And this is the hierarchy of the bytecodes, okay? And every bytecode has an assemble method where it says how to do it. So the push association pushes a literal indirect, okay? So we have a sheet that works all implemented in Smalltalk, like Smalltalk wants us to implement it. And we have a GC now. It's only the generational part of the GC. And we'd love to go forward, okay? So, yeah. So what now? For the GC, we have this closure. We have the collection of methods all the methods that are needed to do the GC. So we can freeze a closed GC that doesn't require any external things to run. We don't have that yet for the just-in-time compiler. We want to have that. So we can have a DLL with a just-in-time compiler for this bytecode that works. Well, call it from C, call it from whatever. We're not sure if that's possible. But we want to go forward and implement a mark and sweep GC, and we want to implement everything that takes to do memory management, like new, become, or copies. I don't know. We don't really know what it takes. A lot, we guess. We want to have dynamic method lookups. We do have polymorphism in our frozen code, but we want to have dynamic method lookups, like polymorphic inline cache maybe, or monomorphic call sites, or megamorphic, whatever.
And join. We would like to join the jitter and the method lookup.
Right. We want to put the two things together but we still want to write the method lookup as itself, so we can test different strategies. Okay? And I don't know, whatever life takes us, right? And that's it. Questions? Yes, Elliot.
So, I'm going to presume, and you can tell me whether I'm wrong, and then answer the question. But I presume that the garbage collector has pre-allocated objects and is simple enough that it doesn't need to allocate objects.
No. Wrong. Yeah, I talked about that actually, and but I didn't say what we're doing. We're just lucky so far. Okay. Yes, the garbage collector actually has pre-allocated objects in the old space, and these objects are the remember sets, which is global, so it must be pre-allocated.
Yeah, but also we have temporary space for our use in the garbage.
Yes, we have the old space and the two semi-spaces for the generational, and we have a local space. That's just a Smalltalk space, like a space, and we use that for some temporary arrays. But there's another one. These temporary arrays we can control very easily where they are created because we create them. The block closures are created by the execution of code. So controlling where block closures and the environment for block closures are created is not that easy. So what we might test rather soon, or not, is we think that we can change the global space where new answers objects from, like the new primitive. We can do that. And so if we, from the environment, right? If we control everything, that's easy. But since we are running in a given environment, we can change where new answers objects from when we enter the GC, and then go back to the previous space for new objects. So we change the space during the GC, we change it to a local space, and then we can freely create objects during GC.
Yeah, but
is
also
space implicitly collected at the end of the.
Yes, collected. Collected.
Yeah, collected.
Everything goes.
Yeah, there is also a strong invariant about what garbage collector may have after GC. We can call object actually.
Yeah, some invariants like we can't have pointers to objects recreated during GC from old space.
But you could recursively apply and copy the survivors.
We could, but in theory, everything that we use during GC is temporary, so we shouldn't have any pointers. Any other questions?
Okay, no, thank you.
No questions.
No, thank you.
Sorry.
Thank you. No.